One of the things that you may see them ask, particularly on the free response question, is they may include a related rate in part of a particle motion problem. So we've already done some particle motion problems where like the particle's moving to the left or to the right and all of that stuff. What you'll see a lot of times on the AP exam, there's usually not a full related rate problem. They usually throw it in for a part of a problem, and sometimes it'll be on one of these. So, particle moves along the ellipse, x squared over 9 plus y squared over 16 equals 1. At a certain instant, x equals 2, y is greater than or equal to 0, and dy dt equals negative 3 units per second. Which is true about the value of x at this instant? Okay, and notice what it tells you here. The value of x is increasing at a rate of this. It's decreasing at this rate. So what are they giving you as answers? Like what variable is that? This is dx dt. All of these are asking you about dx dt. Right? So that's what you're solving for here. Because your answer choices are talking about the rate that x is changing. Here, x and y are both changing. So there's nothing you can plug into this equation before you begin. You are going to just go ahead and take the derivative. It might be helpful on this to think of this as 1/9 x squared plus 1/16 y squared equals 1. So your derivative is going to be 2/9 x squared. Oh, good gracious. No square right there. 2/9 x dx dt plus 2/16, or if you want to reduce that to 1/8, you can, y dy dt, and that will equal 0. Now, they gave us several things. They tell us x equals 2, so we have something to plug in there. Dy dt is negative 3, so we have something to plug in here. We are solving for dx dt, so this is good. Do they give us y? It's positive, but they don't tell us what the value is, right? So what could we do to find the y? Plug it into the original. So that will look like this. We'll have 2 squared over 9 plus y squared over 16 equals 1. So that is 4/9 plus y squared over 16 equals 1. I would subtract that 4/9 there. I'm going to skip down here. I was trying to fit it all up there, but it won't work. So I'm going to have y squared over 16. That's going to equal 5/9 there. And then we will need to multiply both sides.
Wait, no,
Why?
no, you're right.
Why isn't it negative?
Because you got to get common denominators. So that would be 9/9 minus 4/9, which would give you 5/9. Because 1 is not in the numerator there. Okay, so we get y squared over 16 equals 5/9. We are going to multiply both sides by 16, which 16 times 5 is 50. 9, is that 90? No, that can't be. Is it 80? 50 and yeah, 50 and 30 would be 80. Yeah. So we get y squared equals 80 over 9. And we're going to square root both sides, which normally would need a plus or minus. But what did they tell us about y? It's positive. So we're just going to say the square root. I'm going to do square root of 80 over 3, where the 3 is not in the square root. Although you could just leave it square root of 80 over 9. I'm probably going to resort to the calculator here for a while. So I can't. Yeah, I'm definitely going to. In fact, if you want to go ahead and do the calculator, I guess we could do that. Because this is definitely a calculator problem with those decimal answers. So square root of 80 over 9. This is going to give us, this is 2.98142. So now we have everything that we need to plug in. So we're going to have 2 ninths times x, which is 2, times dx dt, which we are not going to replace because that is what we're trying to solve for. Plus, I'm going to reduce that to 1/8. Our y is 2.98142. And our dy dt is -3, and this equals 0. And so I'm just going to solve this. It's a pretty simple equation. It just looks ugly because you have a lot of numbers. 2 times 2 ninths is 4 ninths dx dt. And let's just get a decimal for this mess over here. 1/8 times that stuff times -3 is going to give us -1.11803 is what I'm getting. This just gets moved over to the other side. So 4 ninths dx dt is going to equal 1.11803. And you're going to divide by 4 ninths. And I am getting that dx dt equals 2.51558. Which is not an answer choice.
That's probably what I do.
But I made this question a multiple choice question, and I messed something up and went back and changed it. And I don't think we have time to decide if I've messed up here or if I messed up making the question. Let me double check this right here really quickly, and if this is not the problem. I'll try to go back and look at this one and see where I messed it up, whether it was in my answer choices or whether it was in solving the problem. I am certain that my general process is right on this. I think I have messed up adding or subtracting or multiplying somewhere, or my answer choices are incorrect where I messed up when I was making the problem. So I am not sure which one is the issue. Should it be an increasing or a decreasing? If I get 2.151. It should be an increasing because you're getting a positive answer. So obviously it's not either one of these because I've done something wrong, but we just don't have time to find it right now. I'll look for it after class and try to fix it there. Yes?
When you like dealing with things, I thought we were doing so if you do the square root of 80 divided by 3, throughout that 3 decimal point, do it without making your answer wrong.
Possibly. If you do that, you need to keep it in the calculator and don't round it until the very end.
Like, make it that far off, though?
For a multiple choice question, probably not far enough for it to matter. For a free response question, it may, because you have to be correct to 3 decimal places, so even if it threw you off like 0.002, you would be wrong. So, in general, if you have something in the calculator and you're still working with it, you don't want to round it off until you get to the very end of the problem. That's a good question. Okay, for the sake of time, we may have to skip this one and come back to it sometime, because I want to do some of these others. All right, so the fuel consumption of a car in miles per gallon is modeled by, and it gives us this equation, where x is the speed of the car in miles per hour. If the car is traveling at 40 miles per hour and its acceleration is 15 miles per hour, what is the rate at which its fuel consumption is changing? Okay, so I don't know where in the world this comes from. Right here, I pulled it off of another problem another teacher had. They might have made it up. So I changed the numbers just a little bit to make it a little bit different than that problem. But so it takes a lot of research to come up with that. We're talking about somewhere like, if you're doing this, you're probably getting paid a lot of money somewhere. But we can talk about how to analyze it, right? Even if we don't know how to come up with it. So fuel consumption is F. Okay? And it's measured in miles per gallon. And X stands for the speed of the car in miles per hour. If the car is traveling at 40 miles per hour and its acceleration is 15 miles per hour, what is the rate at which its fuel consumption is changing? So when it tells us that the car is traveling at 40 miles per hour, that is our X equals 40. Right? That value is changing, right? We don't know that it's a constant value, so this is changing. But we are looking at this moment. What is acceleration? What variable would that be?
D squared x over dt squared.
Nope. I know why you're saying that, but it is not. In this case, what's x? X is your speed, which we could equate to velocity, right? Velocity is the absolute value of velocity. So acceleration is going to be the derivative of the velocity, which could also be interpreted as the derivative of the speed here for this particular problem. I guess I could change that to velocity to make any of that confusion go away. But so if I get acceleration, it's the derivative of x. Now, normally x is our position, which means we take a first derivative to get speed and a second derivative to get velocity. But because they told us x is speed here, we only need to take the derivative one time to get velocity. So dx dt is going to be 15. What are we solving for? df dt. So we're solving for df dt. And it might be helpful just to call this f instead of calling it f of x here. Although we're going to use the calculator some on this, and we're going to need an f of x, I guess, for that. Well, kind of. All right, so we're going to use the calculator here. And we're going to do, I'm going to type it in. Here. Okay. So we need to take the derivative of this. And when we take the derivative of this, we can't just do f prime because it won't be a related rate if we do f prime. If we do f prime, it'll be the derivative of the function with respect to x, with respect to speed, right? We want this to be with respect to t. So we're going to have to take the derivative by hand, but we can use the calculator to help make it a little bit easier here. So when we take the derivative of f, we will get df dt. Over here on the right-hand side, you're pretty much just taking a derivative. It's just you got to put a dx dt when you take the derivative of anything with a dx, with an x, right? So the derivative of an exponential is itself, correct? Except for this one's going to require a chain rule. We're going to have to multiply by the derivative of that exponent, okay? So we're going to get 6e to the x over 20 minus x squared over 3,000 times, now we have to take the derivative of the exponent. It is probably helpful on that exponent to think of that as 1 over 20x minus 1 over 3,000 x squared instead of the fractions that you're dealing with. That way you won't have to use a chain, you won't have to use a quotient rule or anything. So the derivative of 1 over 20 x squared, what would that be? I'm sorry, 1 over 20. What is the derivative of 1 over 20x? Almost. dx dt. So if we do it in the calculator, it doesn't put that dx dt. The calculator can only take a derivative with respect to the variable that you're using. And then here we'll get 2 over 3,000 x times dx dt. And so we have the information that we need to plug in. We're putting 40 here, here, and here. We are putting 15 here and here, and that'll fill everything in for us. So you can, see, I guess you don't even have to put that f of x. Let's do this times 1 over 20. I guess we'll just plug it in. We got 15 minus 2 over 3,000 times 40 times 15. And over here, let me change those x's to 40s. And let's hope it works. Okay. So we do all that, and whenever we do that, I'll get that same answer I got last time too. Okay, so we type all of that stuff in. We're just plugging those values in. In a real scenario, write that stuff down. Like if this is an FRQ problem, let's pretend it's not, so I'm not going to do that. You would write all of that stuff down. In fact, let's do this. Let's screenshot it right here. Let's put it over here. There's what we typed in. That is our value. And we will get df dt equals 9.103. And the F is your fuel consumption. So that is miles per gallon. And T is measured in hours. So at this point, your fuel consumption would be increasing at 9 miles per gallon every hour. This. Okay, a lot of these are complicated because the equation is complicated, but the related rates part of it is not like all that difficult. You just have to remember to put the dx dt's and df dt's. Okay. All right, we need to do a Boyle's Law problem because this is a good application that we have here. Did I not work that one out on my notes? Oh gosh, this is the first time I've done this one. thought I finished that, and I didn't, so let's hope it works. All right, so Boyle's law states that if the temperature of an ideal gas is held constant, then the pressure of the gas and its volume satisfy the relationship P equals K over V, where K is a constant. In an experiment, gas in a cylinder is compressed using a plunger. The cylinder has a radius of 2 meters. The height of the cylinder changes as the plunger is compressed. When the height, oh gosh, I do remember this. I did work this out somewhere. I think it's on a different sheet of paper. The problem is, I don't know if we have time to do this one. We might need to skip to the next one. That might be a better idea. We're going to come back to that one because Boyle's law is like one I've seen thrown in on some, like I've seen some AP classroom problems where they've thrown it in. But we're not going to do it right now because I don't think we'll get it finished. Let's go to this one, okay? The twice differentiable function R models the volume of rock in a small quarry at time t, where R of t is measured in cubic meters and t is measured in days. The table above gives values of R prime of t sampled at various times during the time interval from 0 to 30 at time t equals 30. The quarry at time t equals 30, the quarry contains 400,000 cubic meters of rock. The equation A equals 1800 R I bet that was supposed to be an exponent. It had to have been an exponent. Gives the relationship between the area in square meters of the surface of the quarry and the volume of the rock in meters in the quarry. Find the instantaneous rate of change of A in square meters per day with respect to t when t equals 30. I feel very confident that that should have been an exponent because I don't know why I would have put that as just multiplied by 2 thirds. So we're going to change it, but I don't have the last two written down here, even though I'm pretty sure I worked them out somewhere. But so we'll see. So let's start with what we're looking for. What are we looking for? It's usually in your last sentence. It's the ADT. So we're finding the ADT when t equals 30. So our equation for A is 1800 R to the 2 thirds here. So if we take the derivative of this, we'll get dA dt equals, let's do 1800 times 2 thirds, and it's going to be what, 1200? This would be a calculator active problem. 1200 R to the negative 1/3. What do I need with it? dr dt. Now, the problem is that they told us t equals 30 days. So we're plugging in a t, but does this equation have any t's to plug in? It does not. So what we need to know is that if we are finding like dAdt is what we're looking for, we're not replacing it. dAdt such that t equals 30 here, we'll have the 1200, we could think of it like this. We could think of R of, well, let me actually do it like this. Let me not put the 30 in yet. dAdt, R could also be called R of t, right? Because it told us up here, it models the volume of rock in a small quarry at time t. T is what you're plugging into R, right? So R is also just R of t, but it is to the negative 1/3 power. Now, dr dt I can write as dr dt, but up here in this formula it's called R. I have R prime of t. That's also the rate of change of R with respect to t, right? Because t is the variable for that. So this dr dt could also be called R prime of t. And those values, if we want to find those values whenever t equals 30, 1200 times R of 30 to negative 1/3 times R prime of 30. Those values can be found from the table, right? So we don't have to do anything special to find them. R of 30. R stands for the volume of rock. What is R of 30? 400,000, right? Because that R is not in our table, but it tells us at t equals 30, the quarry contains 400,000 cubic meters of rock. So, so that is going to be, we'll have our 1,200, we will have 400,000 to the negative 1/3 times R prime of 30, and that is in our table, and it is negative 0.5. Here. So we're going to use the calculator for that. I'm afraid we're going to get something crazy. I might work this one out first. I don't even know if I did this one. I know I did the other one. Don't put commas in Desmos. It doesn't like it. Hold on. How many zeros did I have? No, that's not too bad. Okay. And so we are getting negative 8.14. Three. And this is dA dt. And for units, we'll probably need to just like area is square meters. You probably wouldn't have to put units on this because they give it to you. So it's asking for the instantaneous rate of change in square meters per day. So it's square meters per day here. So your instantaneous rate of change, that area is decreasing in that case. So we will come back and look at a Boyle's Law problem for sure because I think you're going to see one of those. We just didn't have